All right, let's start where we left off. We were discussing the generation of features in the scalar power spectrum. You'll see that the effects on the tensor power spectrum are rather small, even if there are strong deviations from slow roll. So we will not worry much about the tensors, we'll focus on the scalars. Let me just recap a few essentials. I said in slow roll inflation, I'm just retaining the picture I had this morning. We have just moved to the 10th lecture. And in slow roll inflation, you'll have a nearly scale invariant spectrum with a red tilt, as I indicated. And on either on CMB scales or on scales corresponding large scale structure or even scales corresponding to spectral distortion until scales of about 10 power 4 megaparsecond verse or so, there have been various efforts to understand whether features are required or to constrain features. And I also mentioned as to how on small scales, if you want to produce large number of black holes, you need a significant rise in power, which rises to scales of, much after 10 power minus 4, okay, where there are constraints from spectral distortion. You need a sharp rise in power, and you need power of the order of 10 power minus 1 or so for some range in order to produce a significant number of black holes. And I said that we will consider two scenarios that generates features. The first model we were considering is the model due to Sriramkumar, which I've called as Sriramkumar model 2. And it has a linear potential with a sharp change in its slope. And you have two regions of the potential. What will happen is that the field will be initially slowly rolling down the potential. And there will be a sharp change, in its velocity and therefore the slow roll parameters. What happens is that we are assuming V naught to be reasonably large, so that the first slow roll parameter is rather small in this situation. So the potential, it is changing in the potential, but V naught, this height is so high that, it is epsilon 1 is small. And in such a case, I can assume A to be given by the de Sitter scale factor with H naught being a constant. And you expect slow roll in this regime, and you expect slow roll in this regime, and you expect deviations from slow roll as the field changes, crosses this location where there is a change in slope. And what we blindly expect is, you expect scale invariant spectra corresponding to modes that leave during the initial stages when the field is crossing the initial value of the potential. And as you can imagine, its value will be determined by A plus here, and its value will be determined by A minus and probably H naught as well, okay, which is determined by V naught. This is how the spectra will be determined. I will write down explicit forms of the spectra as we go along. So expect a scale invariant spectra. Well, there will be, to be precise, small tilt, because it's strictly not a constant. There is a small slope involved. And there will be a small tilt here. And these two scale invariant, there will be one spectral, scale invariant regime, nearly scale invariant regime with a small tilt. And these two regimes will be connected by some feature, and therefore you will have a step-like feature in the scalar power spectrum. And we need to solve for this. What we're going to do is essentially determine the form of Z. Okay. Remember, we have to solve the Mukhanov-Sasaki equation, right? So what do we have? We have Vk double prime plus k squared minus Z double prime by Z. Vk is 0. Okay. At early times, you expect it to behave like, essentially slow roll, and we will take the, remember, the slow roll parameters are described by some epsilon 1, epsilon 2. Those determine your solutions, but we are going to take the extreme case where those are also 0, so I can carry out a de Sitter-like solution. So during the initial stages, let me call this as Vk1 of eta, the solution is given by 1 over root 2k, 1 minus I by k eta, e power minus I eta. This is the famous de Sitter solution, okay? Where essentially, remember, this was, if you recall, it was 1 over eta squared, 2 minus epsilon 1, something, something involving epsilon 2, etc. I've ignored this and I've retained 2 by eta squared, in which case the solution of this form. And in the sub-Hubble regime, what is the sub-Hubble regime? What happens is that it is k eta, right? This goes away and you're left with 1 over root 2k e power minus I k eta. Okay. And so in the initial regime, until the field hits the slow roll, hits this change in the slope of the potential, you have a solution. Now we need to know the solution thereafter. If you need to know the solution thereafter, I need to determine what is z after the field crosses phi naught. Okay. Now what do we have in the initial regime? We had this, right? N is what? Minus, someone should help me, MPL squared. In the slow roll regime, it was d phi v by v phi. Correct? This is what it was. Okay. So if I'm going to replace v phi by v, right? Oh, no, I'm sorry, v by v naught, okay? Because that is what is dominating, okay? And then what will I have? I have v phi is, what is it? It is just a plus, correct? A plus. So my n, right? Something like n minus ni, okay? It's the initial value is minus 1 over MPL squared, okay? V naught, okay? But V naught is 3h naught squared MPL squared, right? So I can write this as 3h naught squared MPL squared, right? What is it? This becomes phi minus phi I by A plus. This is my solution, okay? I just have to write it the other way around. I have a solution phi as a function of n. Is that clear? This is until the field reaches that change, place where the slope changes. Let me look at my notes to confirm that everything is fine. Okay. Yes. So I can write this as, please keep this in mind. Okay. I need to remove something. I'm going to retain that because I need that. I will erase this. Okay. Please keep this in mind that in the initial regime, I know the solution to the Mukhanov-Sasaki variable. Okay. So what do I have? I call this as phi plus of n, right? And I can write down the solution as phi I, right, minus, okay, MPL squared, okay. I have written in terms of V naught, all right, MPL squared A plus by V naught. I can write this as 3h naught squared MPL squared, okay, A subscript plus n minus ni. Okay, this is what the solution is. Okay, and you can calculate the slow roll parameter and show that, it's small, etc. I will leave that to you to do. Now, we need to solve the equation, the field equation across the potential. I'll leave this as an exercise for you to do. It's not very difficult to do. Remember, this is the field equation. Plus V phi equal to 0. This is the exact equation, right? And what you can do is that I can write it in terms of phi and n. Okay, this is exact. Phi n plus 3 minus epsilon 1 phi n plus V phi by h squared equal to 0. This is exact. This just, all I have done is that change my independent variable from time to cosmic time to number of e-folds. Now, I can erase this too. All right. So what do I have? I can assume I can neglect this, right? And we have seen that this is a constant. H naught is a constant. So I can set H naught. Okay. And V phi is what? Okay. Post, right? Post the, just a minute. Right. After, for phi less than phi naught, I know this. A minus, that's all. Okay. I need to solve for this. All right. So what do I have? Right. Okay. So you need to solve for, let me just see this. Okay. Right. Now, if I set this to 0, okay, actually this is straightforward to solve. And what you obtain is the following. Just let me get this. Okay. You obtain phi minus n to be minus C1 e power minus 3n divided by 3 minus a minus n by 3h naught squared plus some constant C3. Okay. Don't ask me why I call C3 and C1. Well, there is some other constant C2 in my notes. Okay. I hope it is clear. This is apart from this approximation, which is valid because I'm assuming V naught to be small. Okay. And this H naught, H squared has been replaced by H squared. I'm solving this exactly. And it is clear, right? And at large enough n, what will happen is that this will die away, correct? This is effect because of the transition, change in this thing. And what will happen is that this will remain. But this is nothing but this, right? This is my solution in the slow roll. So if I had slow roll here and I had slow roll here, and I ignored the transition, I would have got this solution. And C3 is just, determines what is the value of, phi at n, at some given n. All right. So, and you can, by matching this and this, you can determine C1 and C3. And what you obtain finally is as follows. I'm going to write down the final solution. Phi minus n happens to be phi naught. There is the duster. Okay. Plus, I will explain what delta A is. 9h naught squared, 1 minus e power minus 3 n minus n naught. I will explain what n naught is. Okay. Minus a minus divided by 3h naught squared n minus n naught. As you may have guessed, delta A is either A plus minus A, delta A is A minus minus A plus, right? So let's understand a few things. When delta A is 0, this will go away and I will get this, okay? Which is the slow roll solution in the initial regime, in the later regime. The delta A is leading to this factor, okay? The change in the slope is leading to this behavior. And m naught is the E fold at which phi equal to phi naught. Straightforward to check. This will vanish, phi equal to phi naught at n equal to n naught. So the field rolls down initially, okay? And then as it hits the change in the slope, the point of the change in the slope, its behavior changes. And then this is, exponentially suppressed after n equal to n naught. Is that clear? As it rolls down the potential, it reaches this point at n equal to n naught from some ni, you can set to 0. 0, it starts at some phi I. At n equal to n naught, it hits phi naught. And thereafter, it behaves like this. At late times, n greater than n naught, this dies away, okay? And what you essentially find is that it picks up the behavior is this modulo some constant value, okay? So now what you can do is that you can determine the value of Z, okay, before and after the transition. Okay. Just let me arrive at that. Just give me a minute. Right. So what you can show is the following, okay, is the following. Z of eta. Remember, what is Z? It is A phi dot by H, which is nothing but, what is it? It is, remember, it is A phi subscript n, right? Because phi dot is H phi n. And what is A? A is given by the de Sitter value, okay? What is phi n before the transition? You can calculate easily, okay? Z of eta is A phi n, okay, which is minus 1 over H naught eta. What is phi n? Okay, phi n is, I can get rid of this. It is, there is a minus that comes in, okay. Okay, just give me a minute. Let me. I'm a little concerned about a value. Okay, so you need Okay, so I have what I obtained for Z prior to the transition to be A plus by 3H0 square. Okay, A plus by 1 over 3H0 square. Okay, so this is essentially, I will explain the minus A plus, okay, divided by 3H0 cubed eta. Okay, I have a minus sign. Okay, so essentially for some eta less than eta naught, I have this behavior. Eta naught is the time when it hits the is corresponds to n naught. Okay. Phi n has to be negative, right? Okay. So that is negative. Okay. All right. I'm not able to completely justify the overall minus sign. Okay. I would urge you to A is minus 1 over H eta. Okay. I'm trying to see how I have written. Yes, that's right. Okay. And phi dot is negative, right? I have taken there is a square root involved and taken it suitably. If I use it precise, if I solve for it exactly. Yes, it's minus. Correct. And A is minus 1 over H eta. Yeah, I have written, for instance, minus. Okay. I'll continue with minus. Okay. I'm not able to justify it completely. Well, there is always a, root. It is root of epsilon 1. And I can take phi dot to be negative. So I think the sign does not matter. Okay. Because it is Z double prime by Z and mod Z squared in the power spectrum. Okay. So I have a minus sign. Only thing I can justify is, epsilon 1, root of epsilon 1, I can take plus or minus root. Okay. When I take, remember, epsilon 1 is phi n squared. Okay. I can take one of the roots. I'm taken suitably so that it is of this form. So this is for, as I said before the transition. Okay. That is eta less than eta naught. This corresponds to n naught, E fold n naught. Okay. So let me call this as Z1 of eta. And Z2 of eta, right? So you know this guy, correct? Okay, you know this guy. E power n is like the scale factor. And scale factor is 1 over eta, right? 1 over H naught eta. And what you obtain for Z of eta is the following. Okay. Is minus A minus by 3 H naught cube eta. This is not surprising. This is the slow roll result, right? And then there is this factor, which is A naught cubed, right? Delta A eta squared by 3 for eta greater than eta naught. And we have defined A naught equal to minus 1 over H naught eta naught. That's what this A naught is. Okay. All right. Now, what you find is that, okay, if you take Z prime, okay, if you calculate Z prime, what you obtain, okay, near eta equal to eta naught, okay. In fact, what you will obtain is that I'll let you do this. You get A naught squared, A plus, divided by 3H naught squared minus A naught squared delta A by H naught into theta of eta minus eta naught, right? It's not surprising that because of the sudden transition change in the slope, there is a theta naught appears. And as a result, what you have is that Z double prime by Z happens to be 3A naught, okay, H naught delta A divided by A plus delta 1 of eta minus eta naught. I hope you understand what I'm trying to say. In the limit delta A goes to 0, this delta function disappears. Okay, that is what it means is that there are additional terms. We have, ignored that, okay, and retain this term. Is that clear? Okay, and this change in the slope, no, this is not Z double prime by, yeah, it is Z double prime by Z. Yeah, okay. So what happens is that it leads to a Dirac delta function. The sharp change in the slope leads to a Dirac delta function in this potential. And I presume you have solved quantum mechanics problems with a Dirac delta function potential. What happens is that on either side, so I wrote down what is VK1. That is the Mukhanov solution to the Mukhanov-Sasaki equation prior to the transition. And that was of a certain form. At much later times, during slow roll, what do you expect how do you expect Z double prime by Z to behave? At early times, okay, look, when this goes away, you will be left with this expression. Correct? This is transitory. Okay, it happens for a short period of time. This quickly dies out, and you are left with this term for phi subscript, for phi minus of n. Remember how phi plus of n behaves. It behaves like this. It is just this term, right? When delta A is 0, this solution, they are the same, nothing more. Okay, and at early times, it is given by this expression. And what essentially I had said was that Z double prime by Z will be given by 2 by eta squared. Okay, so, okay, I need to erase this. I presume you have recognized the solutions, okay, in domain 1. Okay, that is eta less than eta naught, Z double prime by Z. Because it is slow roll, I made this approximation, eta squared. Correct? Okay, so therefore, Vk1 of eta is 1 over root 2k, 1 minus I by k eta, e power minus I k eta. Correct? Okay. Now, at late times, let us say we ignore this. Phi minus of n will be given by this. Correct? Okay. In fact, soon after this transition, phi minus will be given by this. So what will be Z double prime by Z at much after, when the field has come down from the value of phi naught? Can you make a guess? It'll be the same thing under that approximation. Is that clear? So essentially what happens is that in domain 2 to be, okay, Z double prime by Z is 2 by eta squared, barring this point at eta naught. Okay, so as a result, I can write my Vk to be the following. Vk in domain 2, eta greater than eta naught to be Vk2 of eta. Can you make a guess? It'll be alpha k, where alpha k are often referred to as the Bogoliubov coefficients, which you may have heard of, e power minus ik eta, e power ik eta plus beta k by root 2k, 1 plus I by k eta, e power ik eta. Okay, and because I have this delta function at eta naught, I determine alpha and beta through the following relations. Okay. Again, if you have studied quantum mechanics, Schrodinger equation with its with a Dirac delta function potential, if you recall, Vk1 at eta naught is Vk2 at eta naught, but the derivative of Vk, right? So what happens is that Vk 1 prime at eta naught minus Vk2 prime at eta naught is equal to, is determined by the height of this, okay? Height of this, or the amplitude of this Dirac delta function, 3h naught delta A by A minus, and then say Vk1 of eta naught. It doesn't matter because they are the same. That's all there is to it. What happens is that, okay, what will it determine? It determine alpha k and beta k. Okay, I would urge you to determine this. Alpha k happens to be 1 plus 3i delta A by 2a plus k naught by k. I will explain what is k naught. 1 plus k naught squared by k squared, right? beta k happens to be minus 3i delta A by 2 delta A by 2A plus k naught by k, 1 plus I k naught by k whole square e power 2i k by k. K naught is equal to A naught H naught, is the mode that or wave number that leaves the Hubble radius at eta naught. Okay. Now, what do we need? We need the power spectrum. How are these alpha k and beta k arrived at? By just solving this different, by just, plugging these expressions in the matching conditions. Okay. All right. Now, how do we arrive at the power spectrum? Okay. So the power spectrum is as follows. Okay. The PS of k is essentially, remember, k cube by 2 pi square, okay, into mod Vk squared by Z squared, right? And Z squared at late times is essentially determined by A squared, okay, right? Remember, Z squared is A squared pi minus N squared. That's what it is, okay? A squared is H naught squared eta squared. That's all there is to it. Now, if you take, if you plug this in, what you will find is that it's just alpha k minus beta k whole squared, if I'm right. You find that this happens to be H naught by 2 pi. You can write it in this fashion. All right. 3 H naught squared by A minus whole squared. That is because there is a phi minus of n at late times will contain a minus, okay, mod alpha k minus beta k whole squared, where mod alpha k and beta k are given by these expressions. That's all there is to it. Okay, so let me summarize what we have done. We introduced this linear potential with a change in the slope. At early times and late times, you expect slow roll. And because of the sharp change in slope, what essentially it does is that it introduces a Dirac delta function in this Z double prime by Z. That's the dominant behavior. Much later and much earlier, Z double prime by Z, in the level of approximation we are working with, we are treating it as 2 by eta squared. It's the de Sitter limit. Okay? In the de Sitter limit, we know the solutions. It is just 1 over root 2k, 1 minus I by k eta, e power minus I k eta. Prior to that transition, that's the only part. But at later part, because of the transition, there is a positive and negative frequency mode. I need to consider a linear combination of them. And I introduce these two coefficients, alpha k and beta k, which are often referred to as the Bogoliubov coefficients. It's a linear combination of the positive and the negative frequency mode. And I determine alpha k and beta k, right, by these conditions. Just that I would have matched the wave function or the Mukhanov-Sasaki variable and its derivative, okay, time derivative. But because of the Dirac delta function, there is this additional term, much like solving a Schrodinger equation and a Dirac delta function potential. Okay, and that's all. That gives me these values of alpha k and beta k. Now, what I do is that I take this solution, plug this in, and you can convince yourself what will happen is that if I multiply by eta squared, okay, right? Or if I multiply by k, let us say I multiply by k eta. If I multiply by k eta, this k eta will go away and there will be a k eta here. Okay, so only this term will contribute. Okay, so what essentially happens is that modulo constant, the power spectrum is of the form alpha k minus beta k whole square. It's a few simple steps for you to convince yourself. I'm not able to write all of them for want of space and time. Okay, and what you can see, what you can show is that the spectrum of this form. Now you can plug these expressions for alpha k and beta k and write the spectrum in terms of essentially delta A, H naught, K naught, and K. But it's just too long an expression. I'm not going to write that down for you. And what you find is that, where is my chalk piece? It is the spectrum. I'm just going to plot the spectrum. What you find is that it is clear that at large K, right? At large K, what is going to happen? It is only, alpha K which dominates. okay? There is no beta k. Can you guess why that happens? Large K will leave the Hubble radius at early times or late times? Late times, right? So essentially nothing. The transition does not affect it. Remember, I drew this potential, correct? I have this potential. I want you to appreciate the physics involved, okay? The math we have gone through. So there are modes which leave here, the modes leave here, right? The modes which leave here, okay, Hubble radius. So if I plot this picture, right, Hubble radius, and so this, let us say this is when the field crosses phi naught, okay? So these modes here, which are leaving the Hubble radius at later times, are well inside the Hubble radius, okay? This is the log lambda p dh. This is log a, which is the n, right? Okay, so these modes are well inside the Hubble radius. They are hardly, their beta k is 0, which means they are essentially in the Bunch-Davies vacuum, emerging from the Bunch-Davies vacuum, okay? And they are not affected by the transition, but these modes are affected by the transition, okay? So what I would urge you, as I said already, the power spectrum, if you plot PS of k, right, around the regime where k equal to, if I plot around k by k naught, which is equal to 1, some transition occurs, it goes like that, it behaves like that. Okay. In fact, it shows some behavior like this. Okay. It comes down. We will talk about this coming down and this behavior in the next example that we are going to consider. This is the scalar power spectrum. Because it is the background reminds of the tensor form, of the de Sitter form. Why did I say? The tensor power spectrum is strictly, or it has a very small effect. The transition has a very small effect on the tensor power spectrum. It remains largely scale invariant. Okay, all right. So this is one example of generating features from a scalar, in the scalar power spectrum due to departures from slow roll. What we will do is that, and there has been, people have investigated whether this suppression of power can help you improve the fit to the data on the large scales, etc. So there is some value in examining such models. Okay. Now, what we will do is that now we move on to models where you have enhanced power on small scales. Well, I can use the Sriramkumar model as well. I can just push it wherever I want here. Okay, this could be Kobe normalized amplitude, and this could be my enhanced power that I require on small scales. But one of the challenges with the Sriramkumar model is that if V naught is large, it takes a very long, it leads to a prolonged duration of inflation, significantly large, okay? And, inflation doesn't end. You'd like to consider a scenario where if you want to enhance power on small scales, okay, you have slow roll inflation during the early stages. There is some departure from inflation, and then there is an end of inflation as well. And we would like to see what are the corresponding imprints, what are the shape of the resulting power spectrum. Okay, this is a good time for me to stop and answer a question or two. Okay, all right. So let's move to the next example. And this example is what is known as ultra slow roll. An example which leads to ultra slow roll inflation. And I'm going to consider abrupt transitions as I have considered in the case of the Sriramkumar model. In this case, I had a potential where the change in slope leads to an abrupt change in the transition. I'm not going to justify my assumptions here, okay? I'm just going to consider a scenario which allows me to calculate the power spectrum. But, there are many ultra slow roll models in the literature, okay? You can take one of them and integrate the background equations numerically, and you will find that the behavior in those models, barring the sharp transitions that I'm going to assume, is going to be very similar, if not exact, to what happens in these cases. So USR inflation. So it stands for ultra slow roll. Okay, this is of course slow roll. So what do we have? We have this equation, phi double dot plus 3h phi dot plus v phi equal to 0, right? Consider a scenario around, you have a potential, but somewhere, in the potential, V phi is 0. Okay. Around this regime, what happens? Phi double dot is minus 3a dot by a phi dot. Right? Okay. Or phi double dot by phi dot is what? Minus 3a dot by a. Right? So what does it imply? It implies that log phi dot is minus 3 log a. Is that correct? Okay. So phi dot is proportional to a minus 3. Okay. And if I have a situation where h is nearly a constant, right? So what will happen? Phi dot squared is what? Remember, what is epsilon 1? Epsilon 1 is phi dot squared by 2h squared MPL squared. Okay, this goes like a minus 6. Right? Phi dot behaves like a power minus 6. So what it means is that if I have a place where V phi is 0, and imagine a situation V phi is also 0. Okay, so what does it mean? It means that for a reasonably lengthy period, okay, around the potential, V phi is small and V phi is also small. Okay, in other words, V phi is not changing much for a reasonable duration of the potential of the scalar field, changes in the scalar field. Now, in such a behavior is often referred to as ultra slow roll inflation. If there is a point of inflection in the potential where V phi is 0 and V phi is also 0, that is the first two derivatives of the potential with respect to the scalar field vanishes, you essentially have a rapid drop in the slow roll parameter. Okay, and what is important is the following. Okay, so we have already assumed h is a constant, which means the background is close to d zeta, very much like what I have assumed. Okay, which is a reasonable approximation if epsilon 1 is small. Okay, so now what happens during this regime? Epsilon 2 is what? Epsilon 1 dot by, what was it? It was d epsilon 1, d log epsilon 1 by dn, correct? So which means that, okay, this is 1 over epsilon 1, d epsilon 1 by dn, right? But this is a minus 6. What is a? A is e power n. So this is proportional to e power minus 6n, okay? So what is this? This is some constant times e power minus 6n, c1 e power minus 6n, 1 over, okay? D epsilon 1 by dn is minus 6 c1 e power minus 6n, okay? So this goes away, this is minus 6. This is the point of interest. So what do you have? You have ultra slow roll inflation. So you can think of a situation, what do you have? You have epsilon 1 of n, okay? So epsilon 1 of n remains constant, let us say at 10 power minus 2 or so, or smaller, okay? And then suddenly epsilon 1 of n goes down, right? How does it go down? It goes like e power minus 6n. Notice the second slow roll parameter is large, which implies the slow roll approximation is not valid, okay? Is not valid. But if it continues to go as e power minus 6n, inflation will never end, okay? So I need a scenario where it comes down and inflation ends at epsilon 1 of 1, okay? So this is nn, okay? This is some transition where n1, okay? This is n2, okay? Or let me call this as eta 1, eta 2, and eta e, okay? In conformal time coordinates, okay? So I'm going to consider a situation like this. And the manner in which I've constructed, there are drastic changes in epsilon 1. So what will happen is that there will be if I construct z double prime by z, there'll be a Dirac delta function at that point, okay? And I just need to pick up those contributions. And now what I'm going to do is as follows. So you can, if you wish, smoothen this, okay, and think of it as emerging from some potential that is given to us. Remember, if I know epsilon1 of n, in principle, I can go back and construct my V of n, okay? I would urge you to see how to, I would urge you to show how to do that, okay? So what do I have? I have epsilon1. Let me see how I have written in my notes. Just bear with me. Okay, so epsilon1, I'm going to write this as a function of A, right? It is epsilon1I over some regime eta I less than eta 1. And then it falls epsilon y A by A1 by A power minus 6. No, it's plus 6. One falls. So this happens between eta 1 less than eta 2. And then I had to make it grow. I have to make it grow. Okay. It falls like minus 6. Okay. In other words, during this regime, the field is influenced by the point of inflection. Okay. And then you have some epsilon1 of A. This is, I hope it's clear, this is epsilon1 of I. And this is what epsilon1 of A is. Right? Okay. No, I'm sorry. Okay. All right. It starts at epsilon1 of A, and then it rises. It rises as A by A2 power Q. Okay. And eta 2 less than eta E. Okay. Is that clear? Q is positive. Okay. And we are going to assume Q equal to 2, in fact. There's no reason. Okay. I mean, I'm just assuming so that it rises and inflation ends. Okay. Now, what you need to do is you need to calculate Z double prime by Z. Okay. And okay. All right. So in this regime, okay, okay. So what happens is the following. The best way of showing this is the following. Recall, we had written this expression Z double prime by Z as H squared times various quantities here. Okay. All right. Now here, what happens here? Here I can assume epsilon 2 to be 0. Correct? Right? Here, okay, you can convince yourself that epsilon1 is proportional to A. So some power of A, and just like you have in this case, here too, epsilon1 is a constant, epsilon2 is a constant. I have just shown here epsilon2 equal to minus 6. Here, epsilon2 equal to 2. Okay, I will let you show that. It's straightforward. Okay, we are assuming that at all times until close to the end of inflation, epsilon1 is of the order of 10 power minus 2 or small, which means that, okay, the de Sitter approximation is remarkably valid. Okay, and what we can show is that here, epsilon1, we are assuming epsilon1I is a constant, which means epsilon2 is 0. Okay, here during this regime, epsilon2 is minus 6. Here, epsilon2 is 2. Okay, it's straightforward to show. And remember, we are assuming it's always de Sitter. Okay, A is minus 1 over H eta. Some H naught eta. Okay, so what happens is that there is only one expression that dominates here, it is epsilon 2, epsilon 3 by 2. Okay, but what is epsilon 3? Epsilon 3 is epsilon 2 dot by h epsilon 2, correct? Okay, and therefore this goes away. All right, so what is happening is that, as you can see, epsilon 2 is 0 here, it is minus 6, and it is 2 here, and epsilon 2 dot is 0 here, 0 here, and 0 here. But it is non-zero at the transition because there is a jump. If you look at epsilon 2, how does it behave? Epsilon 2 is 0, okay? I should have negative values. It goes from minus, it has, I should put a dotted line here. It is minus 6 and it is plus 2 here, okay? All right, and therefore, this is minus 6, this is plus 2, and of course, this is 0, and this is, say, eta, and this corresponds to eta 1, eta 2. Is that clear? So, in the z double prime by z, this picks up a Dirac delta function. Okay? All right? So, you need to have in z double prime by z has two Dirac delta functions, one at eta 1 and another at eta 2. And let me just write these expressions down. Right. So z double prime by z happens to be minus epsilon 2 in domain 2 minus epsilon 2 in domain 1 divided by 2 eta. Okay. And that's because the epsilon 2 is okay, it is just the difference, the change here, okay? And there is a Dirac delta function, delta 1 of eta minus eta 1, okay? And similarly, at this, therefore, what happens is as follows. I'm going to erase this, kindly keep this picture in mind, okay? Kindly keep this picture in mind. So what do I have? I have modes in the three domains, okay? I have Vk1, Vk2, and Vk3. All right? What I want you to appreciate is that in this domain and this domain, it's inflating with epsilon 1 to be very small, okay? So you find that the de Sitter approximation is very valid, okay? But here, it is, it is behaving differently. So the solution is somewhat different, okay? So what you find is the following. I will, in the domain Vk, so let me write down the boundary conditions. I have to leave this as an exercise for you to do. Vk2 eta 1, 2 eta 1 equal to 1 eta 1. And then Vk2 prime, very much like what we did in the earlier case, minus Vk1 prime at eta 1 equal to this guy, minus epsilon 2 minus epsilon 1, delta 1 of eta minus eta 1 divided by essentially 2 eta 1. I could have as well written this as eta 1. Okay, this is what you have. And what are the solutions in the two domains? It so happens Vk1, as you may have guessed, it's slow roll. So I have 1 over root 2k, 1 minus I by k eta, e power minus I k eta. Okay, and Vk2 eta is some alpha k by root 2k, okay, 1 minus I by k eta, e power minus I k eta, plus beta k by root 2k, complex conjugate, 1 plus I k eta, e power I k eta. That's what you have. All right. So what happens? Okay, let me call these as maybe gamma k and delta k. Right? Delta k. It should be delta. Okay, this is what it is. So these conditions will lead to gamma k and delta k will be determined by these conditions. Are you guys with me? Okay. So there are three phases, a slow roll phase, where my de Sitter solution is valid. The second phase, once barring that thing, okay, the de Sitter solution happens to be remarkably valid. Okay, it is just that at these points, there is a Dirac delta function. Okay, you should be able to plug in and show that it all leads to essentially a factor of modulo the change in epsilon 2. As you can imagine, this epsilon dot depends on the change in epsilon 2. This is 0 to -6. Okay, and this is a -6 to +2. Okay, times a Dirac delta function. And again, like the Schrodinger equation with the Dirac delta function potential, I need to match them. And similarly, I'm going to, want of space, I'm going to write this here. Okay, so what will I have? At the next regime, I'll have the same thing. This -2, and instead of eta 1, I'll have 2, 2, and everything will be the same. 2, 2, 2, 2, 2. Okay, this is regime 3 and 2. This is regime 3 and 2. And this is regime 3 and 2. Is that clear? Okay, but there is a difference. Okay, so now what you will find is the following. I need to squeeze, oh goodness. Okay. So in regime 1 and 2, it is determined by 2 by eta squared. Okay, but if I recall correctly, if you calculate this for, what is this? This is a squared. Okay, so if I recall this, it is 6 by eta squared. Z double prime by Z is 6 by eta squared. Is that correct, Raga? Okay, so what I'm trying to say is that in these two regimes, okay, in these two regimes, Z double prime by Z is 2 by eta squared. In this regime, okay, Z double prime by Z is 6 by eta squared. This is not surprising because look, epsilon 1 is not a constant, it's rising. Remember, this is the third stage, it is rising to end inflation. Okay, so it is different, and I'm just going to, I need to erase this and write the solution. And if I recall correctly, I will have Vk3 of eta happens to be 1 over 2k. And again, there will be some alpha k. I don't recall the complete solution. I need to. Right, it is of this form. Eta plus beta k by root 2k, right? 1 plus 3 by k eta minus 3 by k square eta square e power plus ik eta. These are the solution in the third regime. So these two quantities, alpha k and beta k, are determined by this. And as you may have guessed, alpha k and beta k will be related to gamma k and delta k that you had. Okay, and now you can evaluate the power spectrum at late times. Okay, the power spectrum at late times, I'm just going to write this. You got to work it out. And again, I'm just going to highlight the features of the power spectrum. Okay, so what is it? It happens to be PS of k happens to be, it is 9h squared by 8 pi square epsilon 1 of A. I hope that is correct. Oh, no, this is not good. All right. Okay, no. This is the asymptotic forms. Oh, no, this is correct. Okay, so it is k by A2 H naught. Okay, remember H naught corresponds to the de Sitter value scale factor, whole 2 or minus 2. Let me check this, minus 2. Okay, mod alpha k beta k whole square. Okay, it's not very easy to understand the spectrum from this analytical result because I haven't written the form of alpha k and beta k. It's fairly messy. It's long. I'm not going to bother to write that expression. But you should be able to guess the form of the power spectrum. So you have, let me draw this regime here. okay, and draw the power spectrum here. Okay, I need a little more space. Yes, okay. Epsilon 1 of n, right? So you have this behavior, sharp drop, and then a rise. So this is some epsilon 1 of A, this is epsilon 1 of I, and this is 1, and this is epsilon 1 of I, which is of the order of, let us say, 10 power minus 2 or so, for a good fraction of the time until this time, okay, until this time, the de Sitter approximation is very valid because epsilon 1 is extremely small. Okay, as far as scale factor is concerned. So during this regime, A of eta, I can write this as minus 1 over h naught eta. Now, what's going to happen? There are modes which are going to leave the Hubble radius during this regime. There are modes which are going to leave the Hubble radius during this regime and then during this regime. Okay? And what one finds is the following. Okay? Let us say this is some K1 corresponding to eta 1. This is K2 corresponding to eta 2. Okay? So because this is 2, right, you can show that at very late times, this grows like A squared. Okay, that's what I meant. Okay, remember, this is epsilon 1 is, epsilon 2 is plus 2. This goes like A power minus 6. Okay, all right. And if you plot this as a function of n, right, this is, what is it? That's correct, right? E power, it will have e power minus n. Okay, I should have plotted logarithm of minus n. Okay, so this is a log plot, right? So it is a log plot. So this has a slope of minus 6 and a slope of plus 2. You understand what I'm saying? Epsilon, sorry? That's right. Right. So epsilon is e power minus 6n during this regime. Okay, so I'm plotting logarithm of epsilon 1. Is that correct? Yes. Okay. So logarithm of epsilon 1. So this corresponds to epsilon 1 equal to minus 2. So this is log of epsilon 1 of n. Okay. So this has a slope of minus 6 and this is slope of plus 2. Okay. So because it is plus 2, you can show that the power spectrum at large k, okay, has a slope of k minus 2. Okay. K minus 2. And what essentially happens is that modes that are leave this Hubble radius, okay, you can show, okay, you have to plot this. I mean, it's not, unless you work through it, you will not be able to generate these insights. What you will find is that there is a nearly scale invariant part correspond to modes between K1 and K2. Okay, so this is K1, K2. And here there is a sharp fall. And that's a behavior, there's a famous proof, and it goes like K power 4. There is a rise. Okay? And there is a regime here which is scale invariant, which corresponds to modes that leave the Hubble radius at very early times. Okay? And in between, you can show that there is a sharp dip. Okay? And if you have a smooth potential, so you can have a situation where the power spectrum is like 10 power minus 9 here, and if it's order of 10 power minus 1 or so. Okay, so the rise is k power 4. It's scale invariant, and you can show that it is scale invariant because epsilon 2 is minus 6 in that regime. And then there is a k minus 2 behavior at the very end. And in realistic scenarios, what you will have is that I don't have another colored chalk. This is smooth. It'll go like that. I'll turn like that, fall and fall like that. And that's the kind of spectra that you obtain in ultra slow roll inflationary models. And we have been able to broadly reproduce those features, the scale invariant part, the dip, and even a null at that point, a k power 4 rise, and whether what happens at the peak depends on how small epsilon go to, how negative epsilon 2 goes, okay? And then this k minus 2 is because of the manner in which we have assumed epsilon 1 to rise as a squared as it approaches unity to lead to end of inflation. Okay, but this can fall differently, depending on different inflationary models. So I have considered, just to summarize this part, I have considered two different scenarios to generate features. One, I included by hand, introduced a feature in my potential, which led to a feature in the power spectrum. I have assumed abrupt changes in the potential so that, it is that change in the sharp change in the potential and the Dirac delta function, is largely responsible for the feature in the power spectrum. In the second part, I discussed the currently popular ultra slow roll inflationary scenario, where you have an epoch of slow roll, okay? And then you have an epoch of ultra slow roll where the epsilon 1 decreases exponentially. And then epsilon 1 has to rise, it cannot continue falling. It has to rise, leading to the end of inflation. And I have assumed some form of fall and some form of rise to derive the spectrum that will arise in such a scenario. For the kind of parameters that I work with, what you have is a scale invariant part, a generic K power 4 rise. This is a paper by Subodh Patil and others, okay? And then there is a part where there is a peak, and the shape of the peak will depend on the nature of epsilon 2, value of epsilon 2 at the bottom, when epsilon 1 reaches the bottom. And then this fall, whether it is K minus 2 or whether it will fall faster, depends on the manner in which, after the epoch of ultra slow roll in the given inflationary model, the field rises, epsilon 1 rises, leading to the end of inflation. So I will, for want of time, I'm not able to comment more about this, okay? And I need to take up reheating now. I would like to take 2-3 minutes to comment about reheating before I close for today. But before that, I can answer 1 or 2 questions that you may have. I should emphasize all the analytical calculations are fairly simple. A mathematical code will derive you, get you the values of alpha k, beta k, etc. in a matter of minutes, okay, matter of seconds, okay? And even the power spectra are all easy to arrive at. So these two models are very easy to understand. And if you're going to look at features in the primordial spectrum for whatever reason, please make sure you work through the steps that I have indicated. Questions? Yes. I will talk to you about that. I don't look at it that way. Okay. So I have defined my vacuum state. That's it. It is just my mode functions change. Remember, my power spectrum is just mod Vk squared by Z squared. It is just that Vk and Z are changing. So you can interpret this as particle production and so on, but that is just a matter of interpretation. As far as I'm concerned, there are deviations from slow roll, and my vacuum state, we are working in the Heisenberg picture, that doesn't change. And, in the Bunch-Davies vacuum, this is the form of the spectrum. Okay, all right. So if I want to talk in terms of particle production and so on, in terms of how many particles have been produced, I need a late time asymptotic behavior. I don't have that in inflation. Okay, all right. So that interpretation, you can do that, but it is not necessary. Any other comments, questions? Okay, so I'm just going to take just 2 minutes, okay, because I have a very sharp cutoff, and because I needed to go into this into the epoch of reheating, at least a lecture back, I'm well behind. So reheating. What is reheating? So let's take a simple potential, right? It could be any potential, right? Whatever potential you're considering, V of phi, okay, phi. And we know that this is where phi n, that's where inflation ends. So what do we need to do? I already mentioned that how during inflation, if you calculate what is AE by AI, okay? What is AE by AI? AE is the scale factor at the end of inflation. AI is the scale factor at the beginning of inflation. This we expect it to be of the order of e power 60, which is like 10 power 26 or so, okay? So if I have radiation in the universe, we saw how the temperature of the radiation goes as 1 over the scale factor. So if I have temperature, this what it leads to is that T end is what? Okay, Ti divided by A. So if I have any radiation in the universe, it has cooled tremendously by the end of inflation. So what do I need? I cannot afford to do that. Okay, what is the assumption we have? That the temperature of the universe at the end of inflation has to be very high, sufficiently high. In fact, where it started with. Otherwise, I'll mess up the hot Big Bang model. So what do I need to do? At the end of inflation, I need to transfer the energy to radiation. And this phenomena of transferring the energy is what you do. What you do is that you reheat the universe. Universe is cooled down tremendously. You need to reheat the universe. And where is the energy going to come from? You have an enormous potential energy. Okay, this potential energy has to be pumped into my radiation to lead to very high temperatures, sufficiently high temperatures from where we started off. I have to ensure that TE is as close to TI as possible. And this phenomena where I transfer the energy from the inflaton to radiation is called reheating. Now, what one can do is that one can ask what will happen to the field at the end of inflation. So in other words, the equation of motion for the scalar field that I had, phi double dot plus 3h phi dot plus v of phi, right, equal to 0. I mean, I have inflation has ended, so my slow roll approximation are all out of the window. Okay, so what will happen is that the field will come here, okay, and it'll oscillate at the bottom of the potential. Okay, it'll go back and forth. Okay, as it oscillates, I need to set up a mechanism. I need to couple the inflaton to radiation. I will, for simplicity, treat the radiation as a fluid, and our goal is to transfer the energy from the inflaton to radiation. And what you expect is that there will be a transitory period, but at late times, the energy in the inflaton should decay away, all right? And the energy in the radiation should rise, okay? So that, and then it should fall as 1 over A power 4, corresponding to radiation domination. And we will achieve that, by coupling the inflaton to radiation by hand and transferring the energy. And we will also try to understand what will be the average equation of state as the field oscillates at the bottom of the potential during reheating, because we'll require that to understand what happens to gravitational waves as it passes through the phase of reheating. With those remarks, I will stop here. We will discuss that at the start of tomorrow's lecture. Thank you. Raga, are there questions?
There is one question asking for references. So if you can find
I will update the references. Okay. I don't know whether I will be able to do it tonight, but I will certainly do it immediately after the lectures, and I will update and share it with you, and you can in turn share with all the participants. Thank you.